In this video, we're going to look at electromagnetic induction as induced EMF. Now, we have already seen that a wire carrying current produces magnetic field around it, and that a magnetic field exerts a force on a moving electric charge or a piece of wire carrying current. Now, the question now is, do magnetic fields produce electric current, since electric current produces magnetic field? On that, two scientists, Joseph Henry and Michael Faraday, separately, independently, in 1831 found that a changing magnetic field actually gives rise to an electric current. Although Joseph Henry made the discovery first, but Michael Faraday published the results before him. So because of that, electromagnetic induction was credited to Michael Faraday. Now, in his experiment, Michael Faraday simply connected coil to a galvanometer and brought in a magnet to it. If you put in this magnet into it, you will notice that once you quickly put in this magnet, this is the north pole, south pole, into this coil, the galvanometer will read, you should see deflection. But once this magnet becomes steady with respect to this coil, there will not be any deflection on the galvanometer. And also, if you quickly remove the magnet, if you remove it, there will also be deflection. The only thing is that it will be in the opposite direction to the magnet. Now, Faraday concluded that steady magnetic fields do not induce current in a closed loop or circuit, but changing magnetic fields produce current in closed loops. So, a changing magnetic field produces induced electromotive force. That's EMF. So, we look at Faraday's law of induction. This law states that the induced EMF A in a circuit is equal to the negative rate at which the flux through the circuit is changing. Okay, so if the change of flux is in Weber per second and the EMF is this, we can say that the EMF is equal to, remember it is in volts, it is equal to negative d flux B over dt. Of course, if we have n as number of flux, or not, sorry, number of turns, we can have that E is equal to negative n d flux B over dt. Okay, so this is Faraday's law of magnetic induction. Okay, this entity measures the flux linkage in the device. Okay, so, and remember that this is the magnetic flux and it is giving us B dot A, or you say B dot A cos theta, where theta is the angle between the field and the normal to the surface. A is the area of that surface. Okay, so because of that, the above equation can be rewritten as E equal to negative D into BA cos theta over dt. Or you can add n, you can say E is equal to negative n d into BA cos theta over dt. This question says, the magnetic flux through each loop of a coil of 60 turns increase according to the relation this. T is in seconds. What is the value of T? at an instant when the induced EMF is 1.86 volts. Now, going straight to solve, the number of turns N is 60. That's the number of turns, 60. The magnetic flux is given to us as this. Okay, and the EMF is given to us as 1.86. Okay, we need to know that the total flux through the coil is this, and it is equal to 6. Let's bring this times 10 raised to power minus 3 into 60 plus this. So if we resolve this, we're going to get 6 times this, we're going to get 0.36 t squared. This multiplying this also, we're going to get 0.42 t. Now, we know that E is equal to negative. The negative is just the direction, remember. So d into n flux dt. What it means is differentiate this. So that is this. Now we're going to differentiate this. It means 2 times 0.36. So we say 2 times 0.36. 2 minus 1, 1. So 1t. Plus, here is only 1. 1 times this. 1 minus 1, 0. Anything raised to the power 0 is 1. So we'll have only this there. So if we resolve further, we're going to have that E is equal to 0.72 t plus 0. This times this will give us this. This times this will give us 0.42. Now, but in the question, they told us that E is 1.86 volts. So because of that, we can now say that 1.86 volts is equal to this 0.72 t plus 0.42. So here, this is what has the t that we're looking for. We need to take it to this side and say 0.72 t is equal to, having that this crosses over and becomes minus, so we'll have 1.86 minus 0.42. And if we resolve that, we're going to have that 0.72 t is equal to this minus this will give us about 1.44 approximately. So if we have that, therefore we can make t subject of the formula. Therefore t becomes 1.44 over 0.72. And if we divide that, we'll have 2 seconds. So t is equal to 2 seconds. So the minus sign in the formula was explained by Heinrich Friedrich Lenz's law, which is Lenz's law of induced EMF. So, it says that it indicates the direction which the induced EMF acts. So, Lenz's law states that an induced EMF always gives rise to a current whose magnetic field opposes the original change in the magnetic flux. So, we'll stop here. Remember to subscribe to this channel if you haven't.